Solution stoichiometry. This comes right on what we were talking about with molarity. In solution stoichiometry, we can use the molarity of the solution to convert between moles and volume instead of needing to use the molar mass. So what was our plan, our path for stoichiometry? Starts with grams. Grams to moles to moles to grams, right? So grams to moles to grams. This is a variation. Instead of starting with a mass, we're starting with a volume of a solution. If we know the molarity, we can use the molarity to convert the volume into moles. So this is a variation at the beginning. At the end, we can use this to find the volume of a solution of a known molarity. So this is just a variation on a theme. What's the same is in the middle, the mole-to-mole conversion that uses the chemical equation. So let's do an example. What volume in milliliters of a 0.150 molar HNO3 solution will completely react with 35.7 milliliters of a 0.108 molar Na2CO3 solution, according to the following balanced chemical equation? So what I've been trying to teach you is read all the way through the question and then go back and pull out the numbers and identify what those are. In stoichiometry, we have a balanced chemical equation, and we can use this equation to organize these numbers. So here I've got 0.150 molar HNO3. I'm going to write this below HNO3 in the equation. So 0.150, and what does that capital M stand for? Molarity, which is units of moles per liter. So this is moles over liters. I encourage you to write it as moles per liter because then you are more aware that it is a fraction. Next number we come to 35.7 milliliters of sodium carbonate. So I'm going to write that over here, 35.7 milliliters of that solution. And they also give us the molarity, 0.108 moles over liters. Any questions? What are they asking us to find? The volume of HNO3. So question mark, and it says milliliters. I changed the color there slightly. Hopefully it's easier to see on our crummy screen today. So all stoichiometry problems can be approached using dimensional analysis. And so we have all these numbers, and the thing is we have to know where we're starting. This is the question, so we're trying to find out something about the nitric acid. We must be starting with something about the other thing, the sodium carbonate. And then we look at the units. This one is just milliliters. This one's moles per liter. This could be used as a conversion factor. This one cannot. So we're starting with this volume. So what we're going to do is we're going to be starting with milliliters of sodium carbonate. And we want to end up with milliliters of HNO3. Somewhere in between, we're going to have moles. Moles of sodium carbonate to moles of nitric acid. I'm going to do this example a little differently than I did it yesterday for the Tuesday-Thursday class. so that you have two options, because you can go back and look at that video on YouTube, or you can use this one. So what I did yesterday is we just kind of suspended the milli at the beginning and the end, and we kind of dealt with it later. Today, we're just going to deal with it right off. So to get to moles, we have the molarity, but that involves liters. And what we're given is milliliters. So we need to go to liters of sodium carbonate, and then we can get to moles. And then coming back, I didn't leave much space here, we need to go to from moles to liters of nitric acid, and then to milliliters. This involves more steps, but some students find it more straightforward. There's less thinking involved, and sometimes just you know what to do and you just plow through it instead of getting confused. That would be a good thing. So any questions about the path? We're doing a volume to moles to moles to volume. So we've got the path figured out. Now we're just going to write in all the little steps. So I've got 35.7 milliliters of sodium carbonate. And I need to convert that to liters of sodium carbonate. And then to moles of sodium carbonate, and then to moles of nitric acid, and then to milliliters of nitric acid, and then I ran out of room. So I'll put it down here. Not ideal, but to liters. Wait, I did that wrong. I'm going to liters first. That's better. And then milliliters, HNO3. Well, let's make sure I did that right. Here's our written out path. Milliliters to liters to moles to moles to liters to milliliters. Milliliters to liters to moles to moles to liters to milliliters. So I had a little goof there in the middle, but I straightened it out. Now put in the other units. I need the milliliters of sodium carbonate to cancel out, so I'm going to write that down here. And those units are going to cancel. And then I need liters to cancel out. And then I need moles of sodium carbonate to cancel out. And moles of nitric acid to cancel out. And finally, liters of nitric acid to cancel out. Any questions? All the units in place first, and then go looking for numbers. The mole-to-mole ratio comes from the balanced chemical equation. In front of sodium carbonate, there's an understood 1, and so in front of sodium carbonate down here, I'm going to put 1. In front of nitric acid, there's a 2. This tells me that I need 2 moles of nitric acid for every 1 mole of sodium carbonate. So I'll put a 2 in there. When we did stoichiometry last week, we had to do a lot of calculating of molar masses, right? To go from grams of reactant to moles, we had to do the molar mass. With molarity, the molarity is going to be given to you because they need to tell you what the solution concentration is, so you don't have to calculate molarities. So in many ways, these problems are easier. So this moles per liter here, that's the concentration of that solution, 0.108 moles per liter. And as I often did, I didn't leave enough space, so I'll stick it in there like that. 0.108 moles per liter. At the other end here, liters of nitric acid in moles, that's the concentration that was given here. 0.150 moles for every liter. So for every 1 liter, I've got 0.150 moles of HNO3. Any questions? It's getting kind of small up there, I'm sorry. What about milliliters to liters? What does milli mean? 10 to the negative 3. So milli is in the denominator. I'm going to write what it means in the numerator, 10 to the minus 3. So 1 times 10 to the minus 3 liters is the same as 1 milliliter. And then I'm going to use that same conversion factor, well, the same similar relationship over here. 1 milliliter is still 1 times 10 to the minus 3rd liters. But this time the number's in the bottom because liters in the bottom. So this whole conversion factor and that whole conversion factor would cancel each other out, wouldn't they? That's what I did in the other lecture. So if you want to see that method, you can watch that part of the video. So now we just need to get out our calculators and do this calculation. So 35.7 times 10 to the minus 3 times 0.108 times 2 divided by 0.150 divided by 10 to the minus 3. And our answer, due to 3 sig figs in the volume, 3 sig figs in the molarities, our answer should have 3 significant figures. And so it's going to come out to 51.4 milliliters of that nitric acid solution. Any questions? Problems like this are why I wanted you to learn dimensional analysis. It's hard to just think your way through problems like this on an exam. Any questions?